Can't see your face right now, but can see the board really well.
You can't see my face?
There you go.
Hi, Dr. John Belkowitz here. We got our Concrete Coffee Talk here. We're doing a how-to on teaching your kids about maximum moments for simply supported beams. I've been working with a point load. Are you still seeing me and hearing me good?
Yeah, you're good.
I've been working with a point load. The last time we did the reactions at that point load, and today we're going to be figuring out the maximum moments. So last time we worked on the shear diagram, and we figured out that the reactions for a 100-pound load is 50 pounds at each reaction, and of course there being what's it called, no force in the x direction, or AX at that reaction point at that page. So this time we're going to work on this maximum moment. We're going to do it for a distributed load, and then we're also going to do it for if we have time today, we'll do it for, or we're doing it for a point load, we'll also do it for a distributed load. So there's an easy equation you can get out of a lot of books, which is just the M max. See, they can't see me if I do this.
What do you mean?
Watch. M max equals PL over 4. See that now.
I can see.
So, can you still see me?
Yeah.
Okay, good. So for my load here, it's 100 pounds. My L is 10 feet over 4. My M max from that equals 500 pound-feet. And that bad boy goes right here. Okay, so wouldn't that be great if it was all said and done? But remember, the beam and the shear and the moment diagram, they have to tell you a certain story. We went over, and I just wanted to not just give you the equation, just memorize it, but also try and use the story from the beams that we wrote to give us that information too. Now, it turns out that, and Whitney, correct me if I'm wrong, but the shear diagram, the moment diagram is an integral of the shear diagram. That means the area under this curve right here is going to relate to that maximum moment. Yeah, once in a while I get things right. And the other thing is, and we talked about this last time, this constant positive slope is going to reflect the instantaneous value on the moment curve. So you can see that we have a constant positive value here, and our slope, so our value here is going to be the slope, on our shear curve is going to be the slope of our moment curve. I said that the opposite way, sorry about that. So we have a constant positive slope until we get here, where we have our transition, then we have a constant negative slope, and as you see it right there. So anyway, if we take so we have a shear of 50 pounds here, we have a length of 5 feet.
Mm-hmm.
So with that, we have a maximum moment. Oops, sorry, I did that wrong. A maximum moment, because 50 pounds times 5 feet is 250. What did I say, pound feet? So yeah, that's our value, 250 pound feet. And again, I just got that from the area of this figure.
You need to update that on your right side. You have 500 feet.
Where do I have 500 feet? Oh my gosh.
Or pound feet.
Sorry.
Pardon me.
This was wrong. This is 250. 100 times 100 times, or 100 times 10 divided by 4. Sorry about that. Still a little early in the morning. I haven't finished all my coffee yet. So anyway, the way these shapes change, let me erase these here. The way these shapes change if we go from a distributed load, and we weren't planning this, right? So if we get this wrong, we have to correct me. Whitney will be here. So if we go to a distributed load, right?
Mm-hmm.
Okay, let's see. How do I go to a distributed load?
Just do your bar across.
That's not I'm not an artist, so you'll have to excuse me. But if we do our W, which is what we, our variable for distributing 10 pounds per linear foot, that means we would have an imaginary point load in the center. That is a horrible point load. 100 pounds. But again, remember, it's distributed, and our equation for that is a little bit different. Correct me if I'm wrong. It's M max equals WL squared over 8.
That sounds right.
That sounds right. We'll see.
Yeah.
What we're going to see is now I'm going to use black for my new. So it should be something like, it should be here, and it should be like this, right?
I believe so.
Right, because this is a constant negative slope, so we have the 50 pounds, because remember, we still have a 10 pound per linear foot distributed load times 10 feet, so we still have 100 pounds over the, length of the beam, with an imaginary that it happens like the center of it is at, 100 pounds at 10 feet, or 5 feet, the center of 10 feet. So we're still going to have our 50 pounds reactionary loads that push off at A and B, so we're going to see this push up. Then we have this constant negative slope, till it hits 0. And again, remember, our total is 100. And then again, we hit, if we do 1 foot times 10, here we're going to have, 40 feet, 1/5 of a foot, 40 feet, 30 feet, 20 feet, 10 feet, 0 feet, and then all the way out to negative 50, then we bump it up again to bring it to 0. What's going to happen is, remember, we said that the area under this curve is the maximum on this curve. And because it's the integral of a linear curve is an integral, or is a, help me out, not a polynomial, it's a binomial.
Okay.
So it's going to be parabolic. Right? So we go, the shape that it's going to look like is something like this. That teardrop, parabolic, half circle type look to it. And again, let's see here. Whitney, are you helping out or are you studying?
I'm helping. Yes, go
I
ahead.
felt like you were studying for a second. I would respect that. Whitney's studying steel. So here we have our maximum slope. Here we have our 0 slope, and here we have our maximum negative slope, right?
Correct.
And we approach that from 0. So to get that, again, this is 5, that value, this is 5 feet. So, I didn't do this one. Let me do this one first. So this is 5 feet, and that's 50 pounds. So let's do this equation. Do you have your calculator in? Oh, no, you don't.
No, I think here.
So 10 times 10 squared over 8. I thought you meant your phone. I was like, no, we're using your phone.
I think it's 125.
10 times 100 divided by 8 equals 125. 125 pound feet. Remember, moment is force times distance, so the fact that we need pound feet, not pound per feet, is a good thing. Okay, so let's see if this works out for us. If we could do it mathematically by determining the area under the curve. We've already determined that our instantaneous value on here is the slope on here, and it works out really well for us. But if we take our 5 feet times 50, and because it's a triangle, we have to divide it by 2 to get the area. Dang it. We are good. Wrong color. Turns out to be our maximum moment is 125 pound-feet by taking the area. And the slopes work out, so there you go. There's the difference between a point load and a distributed load, both equaling the same amount. But there you see the different slopes and the different curves for your shear moment diagrams. So let me know if you have any questions. We're going to be doing another live feed today, but it's going to be on concrete mix design, so stay tuned for more information. Thanks for joining us today. Go concrete! There's asphalt.